This chart tracks the accumulation of GDPR fines. By January 2025, that cumulative total reached 5.88 billion euros. A specific fraction of that total came from a 91 million euro penalty against Meta for storing the passwords of millions of users in plain text. Storing credentials without encryption represents a failure of baseline cryptographic storage protocols, independent of the associated privacy violation. For decades, the tech industry has treated digital identity as a persistent static state. A user provides a password once, and the system assumes they are who they claim to be indefinitely, rather than demanding an active, ongoing cryptographic proof of control. Securing infrastructure against data breaches requires abandoning these assumption-based risk models. Identity must be established through strict mathematical proofs. The engineering standard for executing those proofs over open networks is defined by the National Institute of Standards and Technology, specifically in Special Publication 800-63b. The framework centers on the Authenticator Assurance Level, or AAL. The AAL is an ordinal measurement that characterizes the cryptographic strength of a specific authentication transaction. The spectrum of levels corresponds directly to an escalating threat model. Systems must defeat offline dictionary attacks, passive replay attacks, and finally, active verifier impersonation. Progressing from AAL1 up to AAL3 provides the only structurally sound method to mathematically prove a claimant actually controls a token across a hostile network. AAL1 establishes a baseline assurance that a claimant controls an authenticator. This is almost always a memorized secret, commonly known as a password. In its latest guidelines, NIST explicitly deprecates arbitrary composition rules, like forcing users to include special characters, and eliminates mandatory periodic expiration policies. Enforcing arbitrary rules generates highly predictable human behavior. Users simply capitalize the first letter and append an exclamation point, which weakens the overall entropy, or mathematical randomness, of the secret. Instead, the modern mandate requires verifiers to proactively check all new inputs against lists of known compromised values from previous data breaches. To resist offline dictionary attacks, the verifying server must apply a salt. A salt is randomly chosen data, at least 32 bits in length, added to the password before it is hashed. This diagram shows how that plain text input is combined with the 32-bit salt, before passing through a high-iteration loop using a memory-hard key derivation function, or KDF. A KDF is a cryptographic algorithm that derives one or more secret keys from a master key or other secret. This specific model uses PBKDF2, or Password-Based Key Derivation Function 2, which applies a pseudo-random function many times to make brute force guessing prohibitively expensive for an attacker. At this baseline level, security relies entirely on increasing the computational cost for the attacker, rather than taxing the memorization capacity of the user. Moving to AAL2, or high confidence, requires proof of possession and control of two distinct authentication factors. AAL1 contains a critical vulnerability. If a static memorized secret is intercepted while in transit across the network, an attacker can seamlessly reuse it. To neutralize interception, AAL2 introduces a foundational architectural requirement known as reclay resistance. This schematic shows an OTP device combining a persistent symmetric key with a real-time clock to generate a unique, localized output. This output changes every 2 minutes. The verifier checks the timestamp, accepts the value exactly once, then permanently invalidates it. NIST places strict restrictions on utilizing the public switch telephone network, specifically SMS text messages, to deliver these passwords due to structural vulnerabilities like SIM swapping. AAL2 neutralizes passive observation and offline replay. However, because the verifier and the authenticator both hold the same shared symmetric key, the system remains vulnerable to active, real-time network manipulation. That vulnerability enables verifier impersonation, commonly executed through phishing or man-in-the-middle attacks, where an attacker tricks a user and relays a valid OTP in real time. AAL3, designated as very high confidence, mitigates this by mandating the use of a multi-factor cryptographic hardware device validated to FIPS 140 Level 2 security standards or higher. FIPS 140 is a U.S. government computer security standard used to approve cryptographic modules. Verifier impersonation resistance defeats melee attacks. A hardware token establishes a secure TLS connection, locking its output and unique session ID together with a private key. If an attacker forwards the package, their secondary TLS ID mismatches the signed ID, causing immediate rejection. AAL3 architecture also enforces a parallel mandate known as verifier compromise resistance. To achieve this resistance, the verifying server must store absolutely no secrets. It holds only public keys corresponding to the physical hardware tokens. In the event of a total database breach, attackers acquire no usable credential data, neutralizing the threat vector entirely. AAL3 shifts the security model away from protecting shared secrets and toward executing zero-trust, hardware-bound cryptographic proofs. A widespread misconception in the tech industry is that biometric data provides standalone cryptographic assurance. The Dutch Data Protection Authority recently fined Clearview AI €30.5 million for scraping facial images from the internet. This action provides empirical proof that biometrics are public, non-secret data. For network authentication, biometrics contain an inherent flaw. They rely on probabilistic comparisons measured by a false match rate, or FMR. The FMR is the probability that a biometric system will incorrectly identify an individual as a match. NIST strictly limits biometrics, requiring systems to operate with an FMR of 1 in 1,000 or better against zero-effort imposter attempts. There is also an absolute necessity for presentation attack detection, or PAD. PAD is a technical feature used to distinguish between a live human being and a spoofing attempt, such as a photo or mask. This diagram illustrates the final restriction. To achieve high assurance, biometrics must never be transmitted over a network. Instead, they must serve exclusively as a local trigger to unlock a cryptographic key housed inside a physical secure element. In a zero-trust architecture, biometrics function as local convenience triggers to activate actual cryptographic hardware. True identity security is an escalating function of strict cryptographic rigor, not human compliance. AAL1 mitigates basic database guessing through intense memory-hard computational hashing. AAL2 mitigates passive offline interception through localized secret generation and replay resistance. AAL3 mitigates active real-time network subversion through verifier impersonation resistance and asymmetrical public key infrastructure. The rigorous architectural mandates of NIST 863b map directly back to the multi-billion-euro regulatory penalties seen across the industry. Those fines represent the exact measurable financial cost of failing to architect a zero-trust digital identity lifecycle. Securing global infrastructure requires shifting the burden of mathematical proof away from human memory and placing it permanently into dedicated cryptographic hardware.